Good day, everybody. Today we're going to look at vector space of functions, specifically those that are finite dimensional. So for example, I've got x squared, and I don't really care what the coefficient is, so I just made it arbitrary. Then if I take a derivative, I get a new function, some multiple of x. Of course I would get 2 times x, but I don't care what the multiple is. Just this x part, though, that's a new function. And if I take a derivative of that, again I get a new function, times 1. Right? You can't go from 1 to x or x squared with just multiples, so real numbers, scalars. So x squared, x, and 1 are all new linearly independent functions. Whereas if I take the derivative now, I get 0, and that's not a new function. We don't count 0 because I could have gotten 0 just by having, say, c1 0 or anything. So that's not a new function. And of course now every derivative after that is 0. So I stopped getting new functions if I have x to a positive integer like x squared. If it's not x to a positive integer, which I have over here, then every time I differentiate, I'm going to get a new function, right? So I can't get to this function through any multiple of the previous function, and so on. Same over here. So every derivative will give a new linearly independent function. So we can say quadratics, if you include all their derivatives, that makes a finite dimensional vector space. Or here I did it with cubics. So let me try and clear this up here. So if I have a general cubic, so the a1 is not 0, if I take the derivative, I get 3x squared times a1, but we'll just call it some multiple of x squared, and then this gives me a multiple of x, this gives me a constant multiple, and then that goes to 0. And if I take another derivative and another derivative and another derivative, I can represent every derivative through some multiple of these vectors. So this will be our basis. We sometimes call it P3, space of all polynomials of degree less than or equal to 3. And in this space, so even a constant is in this space, or even a quadratic, right? So the derivative is in this space. I put a1 not 0 here just to start, but after that, when I talk about P3, that's the space of all polynomials of degree less than or equal to 3. So this function and all of its derivatives are in that space, and I can use 4 vectors to reach any function in that space. So it's finite dimensional. A few other finite dimensional spaces would be e to a power, that is for e to the ax. Then every derivative is still just some multiple of e to the same power. So this would be a one-dimensional vector space if you include that function and all of its derivatives. All of its derivatives are still just multiples of that one vector. And sine and cosine are also that way. I only put cosine here. So if you take a derivative, you do get a new linearly independent function, but then after that, another derivative takes me back to cosine, and then so on. So I can keep differentiating, and then at that point, all derivatives will just be some multiple of these 2 vectors. So this space is closed under differentiation, and it's finite dimensional. So cosine by itself, sine by itself, or both sine and cosine, as long as they have the same argument, would be in this finite dimensional vector space. Maybe one last pair of functions that are infinitely dimensional if you can count their derivatives. So tangent. So sine and cosine were finite dimensional, but tangent, every time you take a derivative, you're going to get a new function. and arctangent as well. Every time you take a derivative, you're going to get a new function. It's complicated, so I don't want to go through it. Yeah, maybe one more here. I said exponentials, but it was e to the ax. If I tried e to the x squared, then the derivative is a new function. And then when I take the derivative of that with the product rule, you know, this first term was already used, but this second one gives me a new one, x squared. And if I take the derivative of this, I'll get this. So then again, another new function. And then another derivative gives me another new function. So every derivative, you will get a new function. So then this would be infinitely dimensional. So we care about these. If we want to solve a differential equation that's not homogeneous, we sometimes try to do a function that's of that form, but you have to include that function in all of its derivatives. So it won't work if the right-hand side is like t to the negative 1. Because if I tried for my particular submultiple of t to the negative 1, I get these two new functions. If I sub it back into the differential equation, then I get this, and I need a to be 0 and 1 at the same time. Right? So a is sort of overdetermined. And then you can't correct it. Well, what if I had, you know, included t to the negative 2 and t to the negative 3? Well, if I try that for my particular solution, I'm still going to get new functions when I do the derivative, and then second derivative as well. So if you sub in, you've got these new functions, and if you tried to get this equal to just t to the negative 1, which is, you know, all that. Since there's no t to the negative 5th, I would get, you know, c is 0, and then that once c is 0, well, there's no t to the negative 4, so b would have to be 0, so I get a 0 here, and then that would tell me a is 0, and so on, and then I get down to here. Well, I'll skip. I mean, I'll leave that one alone. But then the last equation, a has to be 1. So again, I've got coefficients that need to be two different values. So if you're always getting new functions when you differentiate, you'll never be able to use this method of undetermined coefficients. And I'm not going to cover the method of undetermined coefficients, but I will mention one other thing, and that's, so we've seen this function, e to a constant times t. This and all of its derivatives form a finite dimensional vector space. It'd be one dimensional. And then sines and cosines, that they form a finite dimensional vector space. Polynomials form a finite dimensional vector space. Sums and products do as well. So for example, if I had the sum, then, well, you can just do a vector to cover this quadratic. So you need t squared, t, and 1, and then that would cover t squared and all of its derivatives. I need the vector for e, and then for cosine, I need these two vectors. So my general solution would have to have all of those vectors. So some combination of all of those vectors. Yeah, pretty complicated, but so sums work, and then products similar. So if I just had t squared e times cosine, well, for this vector t squared, I need this general quadratic. For e times cosine, well, I need e times cosine and e times sine. And I didn't look at the derivatives, but if you look at the derivatives, you'll never get a new function once you have these two. So that would be it. So your general solution would include all of those. Another example, if I've got the entire product, t squared times e times cosine, then I need a general quadratic times e times cosine. So I got these three vectors, t squared e cosine, t e cosine, and 1 e cosine. But then I need the same three with sine instead of cosine. So t squared e sine, t e sine, and just 1 e sine. So those 6 vectors would cover that. So sums, products of these types of functions will always be finite dimensional. And that will be it. There won't be any other types that are finite dimensional. Basically, as I write here, if you want a function whose derivative, if you keep taking derivatives, you eventually stop getting a new linearly independent function. Well, what that is saying is that at some point, the new derivative is some combination of all previous derivatives, right? So if you didn't get a new function, then the next derivative is some combination of the previous function and its derivatives. If I change f to y, you can move everything over, and now you have a nth degree homogeneous linear differential equation with constant coefficients. So that's a necessary condition. It has to be necessary and sufficient. So only those types of functions that would be a solution to an nth order differential equation will have a finite dimensional vector space if you include the function and all of its derivatives. Maybe looking more into that. So as a trivial example for t squared, that would be like, it's a little tricky, but it's like r cubed equals 0 or y triple prime equals 0. And then, well, if I wanted exactly t squared, it would have to satisfy those three initial conditions. You can double check. This one you would have been able to solve in Calc 1, right? If y triple prime is 0, you can just anti-differentiate both sides, and that would tell you y double prime is a constant, and then anti-differentiate again, so y prime constant times t plus c2. So this is like a end of Calc 1 when you learn about antiderivatives type problem. Anti-differentiate one more time, and you get a general quadratic. And then with the initial conditions, you would solve, and y of 0 being 0 would tell you c3 is 0, and y prime of 0 being 0 would tell you c2 is 0, and then y double prime of 0 equaling 2 would tell you c2 is 2. And then so the overall function would be 0 plus t squared. So t squared, a quadratic, and t cubed, and so on. So any polynomial is the solution of a differential equation like this. And it can be more complicated than that would just change the initial conditions, actually. A couple more examples. If I have from the previous, so if I've got the quadratic plus an exponential plus a cosine, I would need this for the roots of the characteristic equation. And so this would be the differential equation, and you can figure out the initial conditions so that it was exactly this, if that's what I wanted. Or if for this example, the t squared plus the e, then these would be the roots of the characteristic equation. So this would be the differential equation, and then again you can figure out the initial conditions so that would be the solution. Or lastly, if I wanted this function, then this would have to be the roots. It'd have to be a root repeated, order 3, to get the t squared. And it comes out to be this. So with this differential equation, I would have this function as the solution, and the exact solution depending on your initial conditions. And maybe just a look at that function, and every time I differentiate, I do get a new function. If I put it in vector spaces, where the first component is how many of the t squared cosines e I have, or t squared e cosine, and then the next is t e cosine, then 1 e cosine, then t squared e sine, t e sine, and 1 e sine. So that's how I list the vectors there. So every time you differentiate, you're going to get a new function. You reach all 6 actually after only 4 derivatives, although so now it's not doesn't span, so you actually still get new spaces until you do all the derivatives. I think once I have 6, so once I have the 6 vectors, these 6 vectors are linearly independent. I don't want go too much into that. Maybe I'll just look at the one result. So like over here, if I combine those 6 vectors, I can get this function. Or if I combine the 6 vectors another way, I can get this function. So anyway, so it took the 6 vectors. But the other important thing is, so every time you differentiate, you do get a new linearly independent function, but you're not going to get any new ones after that. All right, so hopefully that made some sense. It's more theory than application, but it might help some. Thanks, and have a good day.